Yep. Yep. Test is coming. We have like 2 sections left. We'll be done with the chapter very soon. Section 7 involves absolute value functions and their graphs. We need to remember what an absolute value graph looks like. The graph of an absolute value function. So yesterday or last time we were working with the graphs of quadratic functions. The graphs of quadratic functions look like what? They are parabolas, yep. The graphs of linear functions look like what? They are lines. The graphs of absolute value functions all look the same to each other as well, because they are all in the same family of function, absolute value. All right? All absolute value functions are V-shaped. Their domain is all real numbers for all of them. To graph an absolute value function, you're going to need to do a table of values, and you need to find the corner of the V. If you don't have the V shape on an absolute value graph, you are not done. So for example, let's graph the basic version of absolute value right there. What would we call that function? That's how you would read it. That is a, kind of like yesterday when we were working with y equals x squared. Y equals x squared was does start with a p, parent function. This is the parent absolute value function. No transformations have been done to it. So, I can set up a table of values, x and y. I probably should pick some negative numbers and some positive numbers. This isn't a step function, so I don't need to worry about decimals so much. I'm going to go -3, -2, -1, 0, 1, 2, 3. Absolute value, of course, means distance from 0. So what is the distance from 0 for -3? How far away from 0 is -3 on a number line? It's 3. How far away from 0 is -2 on a number line? What's happening each time here? Same magnitude, but it's positive, okay? Distance is always positive. So the absolute value of -1 is 1. The absolute value of 0 is, the absolute value of 1 is 1, and 2 is 2, 3 is 3. Pretty straightforward on that. So now we're going to graph those points to see what this thing looks like. -3, +3 is there. -2, +2 is there. -1, +1 is there. 0, 0 is there. Then we have +1, +1. 2, 2, 3, 3. What does that look like? It's a V. So we're going to draw in the V. Just like we've been drawing lines, very carefully make sure that you have this thing lined up correctly. The V has to go all the way through the grid that you're given, just like with your lines. And there it is. All right, so your general steps for graphing an absolute value function are here. First, choose some easy values for x. Watch for denominators to eliminate. Your easy values won't always be -2, -1, 0, 1, 2. You want to pick numbers that make sense for the problem so that you don't have to work with fractions. Then graph it. Remember that you must find the V. If you don't see the corner, you're going to have to try more points. So let's try this one. F of x equals the absolute value of x minus 4. Pick some easy numbers. Do we have any numbers that we should be worried about here, or can we just go with standard easy numbers? Standard easy numbers. What? Why? Let's do -3, -2, -1, 0, 1, 2, 3. And if we run into a bump in the road, then we'll deal with it. Okay, I take -3 and I plug it in. The absolute value of -3 is 3. Then I have 3 minus 4, which is -1. I take -2 and I plug it in. The absolute value of -2 is 2. 2 minus 4 is -2. Then I have -1. Absolute value of which is 1 minus 4 is -3. I take 0 and plug it in. What do I get? -4. I take 1 and I plug it in. What do I get? -3. I take 2 and I plug it in. What do I get? -2, and then finally, -1. So let's plot those points and see what happens. We have -3, -1, which is right there. We have -2, -2 right there. -1, -3 is right there. 0, -4 is right there. 1, -3 is right there. 2, -2 is right there. 3, -1 is right there. What did I get? A v. That shouldn't be surprising at all because this is an absolute value function, and all absolute value functions have graphs that look like v's. So we draw that v in there. Hopefully a little bit better than I'm able to do on my board today. That's the graph. Maybe there's a little buzzer going off in your mind right now. All right, so we don't have any fractions to deal with on this one, so we can just pick normal numbers, right? And probably everybody, when they did this, said x and y, and then they said -3, -2, -1, 0, 1, 2, 3. Right? Okay. Order of operations says take this, plug it in, simplify first, then find the absolute value. So -3 plugged in gives me 0, and the absolute value of that is 0. -2 plugged in gives me what? 1, and the absolute value of that is 1. -1 plugged in gives me 2. 0 gives me 3. 1 gives me 4. 2 gives me 5. 3 gives me 6. So I can plot those points, but I can see from my y values that I never found my v. I didn't turn around and start getting the same values again. -3, 0. -2, 1. -1, 2. 0, 3. 1, 4. 2, 5. 3, 6. All I got was a line. But I know that this is an absolute value function, and it has to look like a v. So I've done something wrong here. Either that or I just haven't checked enough points. Which is it? Need more points. If I keep going with 4 and 5 and 6, is anything going to change? Am I going to turn around and go the other way? No. So I actually need to pick more numbers in the negative department. So I'll go with -4, maybe -5 and -6. This isn't that hard to do that many points, so very quickly. If I take -4 and I plug it in up here, I get -1, the absolute value of which is 1. And now I see I'm repeating. So I just actually started at the corner. If I plug -5 in, what do I get? So the absolute value of that is 2. If I plug -6 in, I get, and the absolute value is 3. So now I can plot those points. There we go. Now I have a v. So I draw in that v. Remember, you need to go all the way through the grid that you're given. So on the left side, I don't have to draw as much as on the right side. That's your graph. So hopefully there's some sort of a little alarm going off in your head saying, hey, maybe I kind of understand what's going on here based on what we did in the last section. Is anybody feeling that way? A couple of you are. Look back at the last two graphs. What can you say about the transformations of the functions that they represent? What happened? Have you seen this before? It's the same thing, yeah. We're dealing with a parent function of absolute value, but it still has the same relationship in the transformations. On the first one, I translated down with that -4, or whatever it was. On this one, I'm translating left with that +3 in the absolute value, okay? Those transformations are still alive with this parent function as well. So for vertical translations, if I want to translate an absolute value function up k units, the absolute value of x plus k. If I want to translate down k units, the absolute value of x minus k. If I want to translate right, I'll have the absolute value of x minus h in the absolute value. And if I want to translate left, what will I have? X plus h. Do you understand now the power of what we did in the last section? As long as you have a parent function, the transformations are all the same. So now you can actually visualize what the graph will look like without even seeing the graph, just by understanding the transformations. Vertical stretches and compressions work exactly the same. If I want to stretch my absolute value so that now it looks like a skinny V instead of a regular V, I'll have a absolute value of X like that. If I want to make it fat instead of a standard looking V, same thing. A absolute value of X like that. If I want to reflect in the x-axis, the negative will go out front of the absolute value. If I want to reflect in the y-axis, I'm going to write this a little bit differently. I'm going to use function notation here instead. I could have been using function notation on all of this. F of negative x still. So if I'm just using the absolute value of x and I want to reflect it in the y-axis, I would write the absolute value of negative x, which actually wouldn't make any difference because I haven't taken the absolute value of it yet. But if I make this a huge function with all kinds of transformations going on, then that negative x inside will reflect it in the y-axis. If the number in front is negative, then you're dealing with a reflection. If you have a number aside from 1, then you're dealing with a dilation. Reflection, dilation, translation, translation. Okay? So the general form of an absolute value function should look very familiar to you at this point. What was the general form of a quadratic function? A parentheses x minus h squared plus k. It's exactly the same look. It's just that now we're dealing with absolute value instead of parentheses and squaring. Okay? Exactly the same. The stretch or compression factor is the absolute value of the number that you see here. I'm saying the absolute value because we're not taking into account the negative sign that might be there. Okay? It's the magnitude of A that stretches or compresses. The vertex is located at h comma k. This is really nice to know because now you don't have to pick test points anymore and try to find where that thing turns around. You know where it turns around just by looking at h comma k. H comma k is your vertex. The axis of symmetry is the line x equals h. So this coordinate right here, h, is your axis of symmetry. Now you don't even have to find points on either side. You find the vertex, you find a few points on one side, and now you have an axis of symmetry that you can reflect over and find your V even easier. So now I've taken it down from like finding 7 points to finding about 3 points, maybe even less than that. Way easier if you understand the transformations. So let's graph this ridiculous looking absolute value function without making a table of values. Where's the vertex? The minus sign is supposed to be there, so that makes this number right here a positive 4. So the vertex is 4 comma 2. So I can put it out there right now. 4, 2 is right there. So that makes the axis of symmetry right there. This thing is flipped over, isn't it? So my V is going to go like this. Answers your question from earlier. It is dilated by a factor of 1/2. So this will look, what, fat or skinny? This will look fat by a factor of 1/2. You can almost consider it like a slope. Without dilation, the slope of those lines is either 1 or -1. With dilation, the slope of these lines will be either negative this number or positive this number. We'll check that. So we need to pick a couple of points. Maybe since I have that 1/2 sitting there, I want to make sure that I wind up with an even number here so I'm not worried about fractions. So instead of going to 3, let's go to 2. If I plug 2 in, I get 2 minus 4, which is negative 2, the absolute value of which is 2. 2 times negative 1/2 is negative 1. Negative 1 plus 2 is 1. So 2, 1, right there. Reflected across. Does that give you a V? Then you're done. Notice the slope of this line, 1/2. Notice the slope of this line, negative 1/2. If you understand that, then you don't even need to do any test points for absolute value functions. This is your graph. And you're done. Understanding the transformations makes life simple, way easier than doing test points and possibly coming up with the wrong answer. Now, I will say that if you don't understand transformations and you try to do this and you do it wrong, you will be assuming a whole lot of stuff and you'll be very, very wrong very quickly. Make sure you understand how these transformations work. For the first one, do we have any translations? No. Where's the vertex? It's at the origin. What's being done to this thing? This is compressed, so it will look fatter than usual. Okay? It's like a fat V. Pick a point. If you don't understand what I was talking about with the slope thing, pick a point. I'll pick 2. The absolute value of 2 is 2. 2 times 1/2 is 1. So at 2, we're at 1. I know this is going to be a V. My vertex is sitting right here, so this is my axis of symmetry, which means I can reflect that across. I have my V. Did I go too far? No. So this is just going to be up 1 over 2 each time. This is going to be up 1 over 2 the other way each time. That gives me my V, and I can draw that in there. The second one, where's my vertex?
1, 3.
No.
Negative.
Remember, you're supposed to see a minus sign there.
I did it that way, but just kidding.
We don't see a minus sign, so this must be a negative 1 to turn that into a plus, which means that the vertex will be at negative 1, 3. That's the trickiest part of these parent function things. You have to keep that straight. After that, it's a piece of cake, I think. Negative 1, 3 is right there. That's our vertex, which makes this the axis of symmetry. All I got to do now is pick a point, and I'll have the whole V drawn already. Pick something that's going to be kind of easy, hopefully. Negative 1 we already have. Negative 2 would work. 0 would work. I like 0 personally. If I plug 0 in, I get 1. Absolute value of that is 1. 1 times negative 2 is negative 2. Negative 2 plus 3 is 1.
Just a reminder, there is a lunch to take you for.
So now that we have this from our vertex, we go down to right 1. We can just repeat that because we know these are lines that we're drawing in. So I can just go down to right 1 over and over and over again. These are V's, which means across the axis of symmetry will be exactly the same dots that I just drew in there. So I'm reflecting all these dots across. And I wind up with that nice V sitting there. It is upside down. It is stretched. It is moved to the left and up. But it's still a V. That's how you do absolute value functions using transformations. Know the transformations. Understand the transformations so you will understand all of these parent functions.